This lecture is about CNNs and visual representation. The objective today is to give you an overview of the type of image representations that are currently used in multimodal, but also give you an overview of other representation that may be not as widely used now, but were centered and very important in computer vision these 15, 20 years ago. So that you have a good historical view on visual representation. Then we will focus a lot more on convolution neural networks and all of its extensions. I really want you to understand the concept of kernels because it is key to this architecture, and also understand how these layers are created and then pooled from there to get some summarization and abstraction. We'll explore some of the extension, some of the original architecture, not the original one from 1990s, but some of the recent one. We'll also look at more region-based CNN. And we have an appendix with a lot of pointers on other ways of analyzing which are non-CNN as well, so that you have more than one approach for this. So that is really important for us. So image representations. If you have an image like this, how would you describe this image? Someone is, what's going on? There's two people talking. There's a third person in the back. There is also, this is probably a diner. And then you probably recognize the character because of the TV show. But how do you go from this image to a representation, numerical representation as we use actively in these neural representation? This is a very hard problem. There's a lot of information in this image. Using all pixels will be overwhelming, although this is, as we've seen, one way we could do, which is just taking all possible pixels and making in one big representation. These days, for good or for bad, many approaches take this kind of image, and the way they will represent it is object-based. They will look at all possible objects in the image, and for each of these objects in the image, will either associate with it a label, a few approach does that, or most of them will in fact have an appearance descriptor. So I have an object here, and I will have an appearance descriptor. And that's appearance descriptor, if someone was to do it manually, we would like it to be very informative, like what is the age of the person? What is the facial expression of that person? What is the body posture of that person? What is the clothing of this person? That's what we would like. In practice, these days, people will take this object and pass it to a neural representation. We'll discuss more what this kind of neural representation like CNN will do to make an approximation of that appearance descriptor. What this appearance descriptor will be as kind of a summarization. You hope that these numbers are in fact a description of what the appearance of that object, although in practice it may be picking up a lot of some useful information and some very high details, like the number of buttons or just the fact that there's a little bit of shadow under the shirt's collar. So there's probably information there that's less useful, some that's useful, but that's what's called an appearance descriptor or feature descriptor. And so an image these days will often be represented as a list of these objects, and for each object, you will have that long vector, could be as long as 2,000 numbers, that is an approximation of what this appearance of this object, both the appearance and also maybe the class label. So this is a great way. This is one way, and it's been very successful because a lot of the work, a lot of the earlier work on multimodal, earlier meaning maybe 5 to 10 years ago, was a lot about object like image description, and these will be very useful to know what objects are in there. I want to also look back at that same image and study, like, how should you represent an object? I told you, and we will discuss in a second more about these neural representation, but I want you to understand a little bit what was the old way, or the conventional way to represent objects. So here I have an object, it's a person. And one way to represent this, and I think it's important because if you really understand what the convolutional kernel in a CNN, it is very useful to understand what were the previous ways images were represented, because these kernels, they do something very specific, and there's a great intuition about it. And so it's good to know how people are representing. So one simple way to take an image like this and saying, hey, let me try to summarize a little bit what's going on in this image, will be to look at image gradient. Image gradient will be the idea of looking here. I have image gradient, which is the X gradient or the Y gradient. And it's easier in this image because the contrast is so big. It goes from white to black. It's looking at changes or variation spatially. We'll call it spatially because in the sense of pixel-wise in the image, in the color, or in this case, it's in the grayscale. So image gradients is very powerful, and in fact, some of the low level of CNN will in fact do something like an image gradient. I'm going to give more example in a little bit, but image gradient is great because it gives you sharp contrast. Every time there's sharp contrast, so it will tell you there's a sharp contrast over here around the eyes and definitely on their shirt. So it will give you sharp contrast. These gradients are also useful for edge detection. That was one of the great success of these early on. If you looked about before 2010, some of the best approaches were in fact looking at these gradients and looking at kind of a histogram of gradient. And here is really interesting because it's doing two things. It's taking the image and it's spatially kind of creating a grid. The grid you can see by seeing all of these points here. It's taking the image and making a grid, and for each grid it will tell you where is the largest gradient or histogram of the gradients, which here I'm plotting the largest gradient. And so what it means is that you can take the concept I want to explain here is that you have a mix of two things. You have variation of the color. This is the gradient, and this is plotted with different angles here. And you also have spatial information because I keep gradient. I compute the gradient at different part in the image. And so you could imagine, here I did it 20 by 20. I could have done it like just a 4 by 4, and for each quarter tell and say where's the gradient going. So this concept is going to come back in the CNN very quickly when we do it with the kernel, but this is histogram of gradient, and there was a very famous one called SIFT feature that extended this. And then I would also like to talk about something we don't see as often in images because you don't have that aspect of temporal, but in video, you also have the gradient over time. So between two images, where are the pixels moving over time? Where's the motion going over time? And that's can be approximated with optical flow. These may be a little bit abstract for you, these concepts. So I want to make it a little bit more concrete by introducing the concept of Haar wavelet. Haar wavelet is the first phase detector, or I would say not the first, but one of the best one in early 2000 was Viola and Jones phase detector was using these Haar wavelets. And the idea here is you have a dictionary of filters and a filter, and I will use the term filter, and sometime I will also, when we talk about kernels, you can also look at this as a filter. And you could almost also see, because filter and kernel may be like concept that you don't use every day, those words, but another way to think about it is just a template. these are templates I'm trying to match on this image. And so here I have a template, and this template is looking for horizontal edges. And so if I take this template and I run it all over the image, and I look for these templates, and I finally find a template like this here, because there is an edge, there is a horizontal edge. Then if I get a response to this, I will run my template all over the image, and every time I run my template, I will say how well does it work, how well does it match, and that gives me a response. And then I get a new image that is called response map. So if I do it with this, I will get what's called the gradient, horizontal gradient. If I do it with this one, I will get what's called a vertical gradient. Now I can do with different oriented gradient. I can do with any kind of these gradients. And so these gradients will give me how often there is an edge this way, how often there is an edge this way. And so when I showed a little bit earlier this histogram of gradient, the idea was that they had a bunch of these different angles, and they were just saying how well these match locally on this image. But you can also get a little bit fancy on your templates, which is a little bit the same as filter and kernels, and go and look at white, dark, white. A very classic one for faces is the opposite of that, is like dark, white, dark. Dark, white, dark is one of the best filter / template that you can do for faces. Where? Here, the bridge, you can get dark in the eyes, bright, and dark in the eyes. And so when the first face detector came in, they had all these fancy hard detector, like different dictionary, predefined dictionary, and then they looked over which one was useful for each object class and for faces. That a version of this was very good. So these HAR wavelets, you can see them as template tested over the image to be able to get a response map. And then you can look at maybe the amplitude of the response map and say how well this different dictionaries will match for this object. These will be related with in a second when we talk about convolution kernels. They're very related to that. And I want to show another one, and you may need to zoom on this to see it. It is called Gabor filter. Gabor filter is almost of a generalization of these HAR wavelet. And why they're so important is Gabor filter, in fact, are inspired with the visual cortex. In early stages of perception, human perception, there is this bank of Gabor filter looking at different edges and different, and then if they see this, then they will light up meaning a neuron will activate. So neurons and the brain is already doing that. So our intuition, if brain and we like neural networks, so there's a good chance that having these templates could be quite useful in representing images. So based on these intuition, this is where this idea of kernels or templates came in. So you can see people naming it slightly different. So in our world of CNN, we'll call them kernels. And so what this means is an image like the one I have here, and then I will have kernels. And earlier, these kernels were very discrete. And that's often what we'll use is very discrete then. Or you can then make them a little bit smoother, like two Gaussian, one's positive and one negative, two Gaussian. And if I run this on my image and I run it all over, I get a response map. And so you can see here, this is the horizontal gradient. And then I run it here to look at the vertical gradient. Or I could go look at this one. This one is kind of not exactly an approximation, but quite related to these two. And this one will look at kind of any contrast or edges will come from this one. So this is the terminology. You have input, you have your kernel, and we'll call it convolution because this is the and we'll discuss mathematically what it means. you could say it's only multiplying it all over, but it's a slight difference on that, like a slight warping, flipping of the kernel over that. But yeah, it is about just multiplying over the image over. That's what convoluting is. And so many approaches over the time these days, many of your projects and many of the papers you will read will be one extension of a convolutional neural network. And I wonder in the next few slides, we'll explain this architecture with this intuition that we just talked about of kernels, but the CNN. And so more details is coming soon about CNN. But I want to give you a little bit more because there's more in an image than objects. And although most of the papers you will read these days, the way they look at it at an image is as a list of objects, images are more than that. And specifically, if you have a face. I mean, if you have a face, then in this case, then you may want to also look at the facial expression in this face. You may want to look at the eye gaze or the head pose of this face. If you have a body, you may want to also look at the body posture of the person. And so what we put in the appendix of this lecture is not an exhaustive, but at least a long list of other ways, specifically for human body and visual behavior related to human, other ways you can quantify. Because right now, if you use a CNN, and we'll talk more in a little bit, but CNN, what they do is they're trained on object detection. A lot of them are object-based, object detection-based. So for them, all of these people are all the same. It's just one big category. But people are very different. We know it very well. There are different emotions, different gender, different ages. And so there's a lot of information that is sometimes not as strongly quantified with current CNN approaches. So I want you to be aware of that. But let me, since they've been very powerful and very helpful, convolutional neural networks are still very helpful. And so I want to discuss them over the next part of this lecture. So one important aspect is why convolutional neural network. What is it they're doing so well? I'm saying they're not doing everything perfect, but they're doing a lot of things very well. And so their goal, because going from the image, one of the internal goal of these convolutional neural network is to build a more abstract, and to do this, they do it in a hierarchical way, a more abstract visual representation of an image. And so the main key advantages of convolutional neural networks, at least 5 of them, I'm sure there's others, but 5 that I believe are worth describing or discussing. One is similar to what I talked about with the Gabor filter. The Gabor filter is that by having low-level representations that are maybe similar, by looking at edges at low-level layers, it is somewhat inspired from visual cortex, because the cortex does have like initial activation, maybe looking at edges. And then after that, although in the brain and cognitive science, there's still work to be done to know exactly what is after these initial, we know that there's some dedicated one for certain objects, for example, for faces. So there is a probably inspiration for visual cortex. One thing about CNN that is great and will emphasize, and you can see it already, at least at a high level here, is that it encourages this visual abstraction where at a higher level, and as you go higher and higher in the models, you get hopefully representation that are englobing a higher level understanding of the image. One thing that I will explain in more details in the next slide is the translation invariance. So this is LP right now talking, and this is still LP talking, and this is still LP talking. The only difference is me just translating. And so although for some application, translation invariance may be like knowing that I'm on the right or knowing I'm on the left is important. In many cases, just knowing that it is LP is the most important. And so being able to take advantage that this is LP and this is still LP, and then I don't need to learn one model of LP being centered and one model of LP being on the right side of the image and another model of the right side. That is something that is we should take advantage in the neural network. The big difference with what we talked about earlier with the Gabor filter and the HAR and the CNN, the big difference is that these templates, these kernels, these templates, it's not a predefined dictionary as previous approaches had done. Instead, it's learning it dynamically. Not dynamically, it's learning it as part of the optimization. These are learned. It's not a predefined set by either a human or that manually did it. It's learned from data. And one thing that's an advantage of CNN over doing the same problem with a fully connected model like a multi-layer perceptron is that it has lower number of fewer parameters, and primarily because of these two. Because of number 3 and 4, then 5 comes from that. So translation and variance, I already gave you an example, but if you want to detect, like, is it LP upside down or not, you can do that. I give you an image of LP, and then you find out, is it an upside down image or not? And you can learn that relatively well with the multi-layer perceptron. Maybe even one neuron may be able to do this task. But then, as I mentioned, there is the idea that if I slightly on the right or the left, you want to still be able to recognize. You don't need to, you should not have to train what upside down means in both cases. And so the model should still be able to classify. Conventional MLP, unfortunately, they're not translation invariants. If you have an object and it's slightly on the left or slightly on the right, it will be almost a new instance for them. Because the way it is by default looking at the image every possible pixel. So, but CNN, the way it will be done is by approaching it from a kernel perspective and hierarchical, will by doing the kernel and running or convoluting it all over the image, what we will be looking is like, for example, when we talk about LP, is maybe he's always smiling, so we're looking for some smile kind of local features, or we're looking at a specific type of hairline, or I don't know what else is typical of LP, what he looks like, but they will look at very local descriptors or templates of what looks like LP, and look in any new image and look for these patterns. That's what we call kernels, or we call templates. And by doing this kind of approach, it helps, both it helps by reducing the number of parameters and also help with translation and variance. So I told you the big difference between this previous work and the CNN is that the CNN will, instead of taking a predefined set of kernels, these as you have many layers of the CNN, you learn your own dictionary. In fact, the big W, if you remember in a linear classifier or a neuron, the W, what will be learned in that W is in fact what this kernel should be. And so you could imagine you start with randomly initialize them. So all of these will be like looking like noise. And as you go on and on, then the network will find what is useful for separating the different classes. And in this case, maybe dogs. We seem to like dogs. And so colors may be important, or different kind of stripe patterns. And so it's great because it will allow to learn this dictionary in an automatic way. And if you have new classes or new labels, maybe the dictionary will be different. And here what you see, and they don't look as intuitive here, but this is an aggregation. It's mostly a template of templates, and we'll discuss more in details. But the low level is looking, and these are very intuitive because they look a lot maybe like something like this. So these are like template, a little bit what would be in your eye, the earlier. And then what it is here is the next level after, okay, I detected all of these. Let me try to look at like more complex patterns on top of that. So in the CNN, we learn these parameters. So just to remember what convolution is mathematically, since this is the core aspect of it. So the most like theoretically or mathematically, convolution is a basic mathematical operation that given two functions returns another function. In our case will be one function, maybe the image, another will be our kernel, and then it returns this other function, which is the response map. This is the high level function. In our case, there will be discrete functions, but this also works. So you have the continuous, and in our case, we'll look at discrete version, which is what we're focused on. So if you have the 1D and you have a 1D image, and maybe everything is dark, and then it's bright, and then it's dark, okay? So it's a 1D here. It's a 1D version maybe of this line. And then there's a kernel that is looking for an edge, any kind of edge. But it's looking for, in this case, because we have only a 1D, is looking for an edge. So it's going from 0 to 1 to -1 to 1 again. And so if I run this, and I use the term run, but if I convolute this kernel on my input, then I get the response map. The output of the convolution is my response map that shows where this matched really well around here, and it matched really well, or matched really well positively, almost, if you look at it as a correlation, very highly correlated around here, or weakly correlated, or negatively correlated around there. So this is like 1D convolution. In CNN, we only consider function in a limited domain. In the general domain, it was continuous. But in the case of CNN, we'll have the signal is a length n, not just infinite. And this is for 1D. And if it's a 2D, it's n by m, or the width and the height. And then the kernel itself, if it's 1D, will have one length. Maybe usually kernels are not really big. It could be 3, 5, 7. They often are odd numbers. And the output will be, it's a simple, the number of output will be the n minus k plus 1. It's just you have to do the test yourself, but these are the number of complete convolution that you can do. There's the edge cases, and there's some little tricks to do there. One example is to just copy over whatever any valid convolution and just copy when you're on the edge. That's an example for that. If we want the output to be different sizes, that's what I was just saying. You can either make the image a little bit larger so that eventually it is the same size. This is an example that you can do. One other thing that you may hear is the concept of dilated convolution or strided convolution. It's just the idea that you skip. So instead of taking the input, you're kind of downsampling the input and then running your filter on this. This is 1D, but in a lot of cases that we'll do it with 2D. So we'll do the convolution in 2D, but the basic concept is the same. So I often call them these convolution kernel templates. And you can see here, this is clearly a template. It's looking like something like this. Do you know the building in the back? Okay. Yes, it's MIT. No. Yeah, I let you decide. No, I think it's okay. I don't know. Okay, that's put it in your summary. Who knows what this image in the background is? Maybe my bias from my PhD at MIT tells me it's MIT. Anyway, so yeah, but you can see the convolution goes and look for this exact kernel here, and you can see the response map is finding it here. But there is a dark and a white, and dark and white also matches a little bit around there. And so that's what the idea of this. I'm just gonna show this example. This is an example of, and you should take the time to look at it in more details, but I just wanted to show this animation. Whoops. So what you see here is you have, sorry, I think you see my pointer. So you have the input image. Here I have it input image as RGB, so R, G, and B. And then I have my kernel. In this case, I have more than one kernel. So I'm kind of generalizing over many things here in this examples. So I talked about only one image and one kernel. But you can have multiple image and multiple kernel. In fact, one kernel, here I have two kernels, and each kernel can have multiple dimensions. So, and so a response, the response map, if I have only one image and one filter, then it's a 2D response map. But if I have a 3D volume, then I have 3D filters. Then I have also 3D, and I have more than one filter. Then I have the response for one filter and the response for the second filter. Even if I didn't have W1, I will not have here this second response. The second response, as you see, is just the second filter. So we'll talk about this, not just about a matrix or a response map. We'll talk about it as a tensor, as a 3D or more matrix. Yes. So this is an example, and you should look at more. This web page is quite good. So convolution neural layer, and this, if you have to focus, like what I want to give you the intuition on this, and this is important because so many people use CNN and don't realize what the CNN is doing, and they just take it as a black box. But we're about to do multimodal. If you take every unimodal representation as a black box, your fusion is not going to use all the intuition it could use. And so I think it's very important to have the right intuition about each modality that you're using in each representation, because that will allow you to make your fusion and your joint multimodal representation more intuitive. So taking an image like this, if I wanted to use a fully connected neural network and learn to predict a response map, what it is I want to give me an image, and I want to be able to get always a response map that gives me looking for detection of this exact pattern. If you remember this pattern that was in this. So I want to go from input to output. So the simplest, not the simplest, but one maybe way you could do is to connect every possible pixel here to every possible location in the image. And every pixel, and so every location, like to answer this, it will be based on all possible pixels. So that's what here, this neuron, the output of this neuron here will be based on all possible image. And the response from this next neuron will be from all possible pixels. So as you imagine, this is not efficient. Even if your image is really small, the number of parameters will be huge. If your kernel was of size n, or if it's even like 2D kernel, it will be a huge number of parameters that you'll have to learn. So, and it may learn different, the most, like the challenge here is that this is not even translation invariant. If I shift this image slightly to the left or the right, this will be completely different from it, because the weight for this pixel may be different for the weight from this pixel. Also, one thing that it may learn is that it may learning a different kernel for different part of the image, because it may end up learning a kernel for this part of the image, but a different kernel for this part of the image. So it doesn't necessarily, there's nothing that forces this kind of model to learn any kernel. By the way, I think there's a little typo here. I will double check it for the next lecture. But yeah.